This lesson is part 1 of section 10.2. Today we're going to be discussing the law of sines and the law of cosines. Our main objective for today is to be able to use the law of sines and the law of cosines to solve a triangle. Now notice that we are missing a word that we typically see right here before triangle, and that word is the right triangle, right? Normally we solve right triangles. Like yesterday, our entire lesson was on right triangle applications. We solved those right triangle using methods like Pythagorean theorem or SOHCAHTOA. That was the main one from yesterday. But we also could use, special right triangles, those 30, 60, 90 patterns or the 45, 45, 90 patterns. So today we're actually not going to be solving right triangles. We're going to be solving just general triangles that are specifically not right triangles. But we use the law of sines and the law of cosines. So again, even though the law of sines and the law of cosines apply to right triangles, we don't need them because we have so many other methods for solving, right triangles, as I mentioned before. With non-right triangles, though, we need to use the law of sines and law of cosines because all those other methods, like Pythagorean theorem, obviously don't hold true in any type of triangle. So anyhow, let's actually talk about what the law of cosines and law of sines actually are. So let's start with the law of sines here. The law of sines says that in any triangle, okay, including right triangles, the ratio of the sine of an angle to the length of its opposite side is constant. So here I've got 3 different ratios set up. These are equivalent ratios to each other. This is showing that the ratio of the sine of A over little a, so the length that is opposite the big angle A. So it's typical in a textbook. This is just standard that when you see big A, little a is opposite big A, the angle. Big B, little b is going to be opposite of big B, and for big C, little c is going to be opposite of big C. So basically all it's saying is that this ratio here, if you compare that sine of A to that segment, A, little a, that'll be the same ratio as if you compare the sine of B to little b and the sine of C here to little c. Now you can also, obviously since they're ratios, you can write those upside down and flip those ratios, write that as little a over sine of A. So I'm going to show you a quick proof of this because it's actually pretty easy. Now the proof starts by just showing the area of this triangle. So if I express the area of this triangle using what we talked about yesterday, I know that I can take any 2 sides and the included angle between those 2 sides and write it as 1/2 the product of those 2 sides. So half of the product of the 2 sides, and since I'm using A and B, the included angle here would be C, so times the sine of C. Now that is equivalent to 1/2. I'm just going to express it in a different way using 2 different sides. Let's use C and A now. So 1/2 of the product of A and C multiplied by the sine of B, since this is now the included angle. And then again, if I want to take another pair of sides here, B and C, I can write that as 1/2 times the product of B and C times the sine of, this time the included angle is A. Alright, so again, this is just the statement expressing the area of this particular triangle. Now the proof is actually just one step. It's kind of cool. I'm just going to multiply throughout this entire, both sides of this equation, or all 3 sides of the equation here. And I'm going to multiply by 2 over ABC. By doing that, if I were to distribute here to every single part here, and I am multiplying on both sides of an equation, so I want to stress that you're not really doing anything. You're not just changing one side here. You're distributing to every single part of this equation. But I end up with, since the 2's will cancel, and that AB term will cancel with this AB term here, I'll have the sine of big C over little c equals, the same thing's going to happen here. Now the AC will cancel and the 2 will cancel, so I'll have the sine of big B over little b equals the sine of big A over little a. So again, one-step proof, kind of cool. Usually they're so long. So now let's get to actually using the law of sines. Okay, right off the bat here, I obviously can use the law of sines because the directions tell me to use the law of sines to solve this triangle. However, just by looking at the triangle, I know that I can apply the law of sines because I have one complete set of information, meaning I have an angle measure and I have the side length opposite that angle. Remember, you need to have at least one ratio set up, so I can set up the sine of 30 degrees over 12, and I can set that equal to any other ratio that I want. So in this case, I could solve for little c here by setting up the sine of 135 over little c. And I could also use the same ratio. Remember, you have to have one complete ratio here. I could use that to solve for the other missing side here, little b. but I have to know this angle measure, and obviously we can take 180, subtract this 135 and this 30, and we end up with 15 degrees here. So I've got another equation that I can set up. So if I want to solve first for C here, I would multiply, cross multiply basically, and I'd have 12 sine 135, so 12 times the sine 135 over the sine of 30 degrees. Now we actually don't need a calculator for any of this because we can just do this using our known trig values here. This is going to give me 12 times, now the sine of 135, this is a pi over 4 family if you want to think of it like that, and it's in the second quadrant, so the sign here would be positive, but it ends up being root 2 over 2. And the sine of 30 degrees, this is right above the x-axis, so that's going to be the smallest value, that would be 1/2. So just by simplifying, probably the easiest way to simplify this, you can multiply by 2 over 2 here. So you end up with 1 in the denominator, and then in the numerator, those 2's will cancel here, and I'll be left with just 12 root 2. So I have C equaling 12 root 2, little c. All right, now to solve for little b, I can set up another ratio. I can use the sine of 30 again over 12, so I'll use this ratio since that's the known ratio here. I could use this one now since I have a complete ratio with sine of 135 over 12 root 2, but I'm just going to use the 12 here instead just because I don't want to deal with the radical. So I have the sine of 30 over 12 equaling the sine of 15 degrees over little b. And if I solve for little b here, I end up with 12 times the sine of 15 degrees over the sine of 30 degrees. Okay, now I want to actually do this calculation here without using a calculator because we know our half angle formulas. So if I want to take the sine of 15 degrees, that would be like taking, that's a half angle formula here, and I can now write that as 12 times the square root of 1 minus the cosine of 30 degrees over 2. And that's all over the sine of 30 degrees, which we know, I'm just going to write that in actually first. Okay, now let's evaluate. So we have 12 times 1 minus the cosine of 30 is root 3 over 2, all over 2, divided by, again here, the sine of 30 is going to be 1/2. Okay, first thing, let's see, probably the easiest thing to simplify here would be to take 12 over 1/2 and write that as just 24, and then in this radical here, I have 1 minus root 3 over 2 over 2. And I'm going to multiply. Again, I'm going to use that same method here, just multiplying by 2 over 2, because that'll get rid of that, denominator here in the numerator. That kind of sounded weird. So I have, let's see, 2 minus the square root of 3 over 4 now. And then if I want to simplify here, I have 24 times the square root of 2 minus root 3, and the square root of this all is under that radical here, and so that square root of 4 here just turns into 2. Then I have 24 over 2, so okay, here we go. 12 times the square root of 2 minus root 3. All right, now I just want to verify with you guys that we did that correctly, that we reduced everything and wrote this in those terms correctly by using my calculator. Okay, so I went ahead and I typed in 12 times the square root of 2 minus root 3, and I got that same exact value as when I typed in our original expression here, that when we solved for b, we had b equals, I know you can only see part of it, but b equals 12 times the sine of 15 over the sine of 30, and then of course we apply that half angle formula here, but we end up with the same value. Woohoo! So we did it right, and now, again, I just wanted to verify that, but really you can do a lot of this in your calculator, but I want you to sometimes be able to get exact values. So when you see something like the sine of 30, the sine of 135, those kind of things, you should be getting exact values. Now in a question like number 2, it's very, very difficult to get exact values here, so we don't expect you to do that. You can find an exact value and then show the approximate value as well. So here, this exercise makes you actually draw the triangle correctly. So I'm going to begin by setting up a pretty tentative sketch of what triangle ABC might look like. And in this case, it really doesn't matter where I start labeling A, B, and C, but when I fill in my information, it obviously does matter. So I've got angle A is 75 degrees, and little a is 10.2, so I want to write that across from big A. Angle B is 62 degrees, which makes this an acute triangle because then angle C would be 43 degrees. Okay, I would like you guys now to solve for the missing side lengths here and then check your answers with the key. Okay, let's move on now to the law of cosines, which states that also in any triangle, the square of the length of any side, so here we are squaring A, okay, so that length here, the square of that length equals the sum of the squares of the lengths of the other two sides. So here we've got the other two sides, the sum of the squares of the other two sides, and then minus twice the product of the lengths of those other two sides. So I've got minus 2 times the product of B and C, then times the cosine of their included angle. So the included angle, cosine here of A, that A is the included angle because we're looking at the other two sides, and so you can actually demonstrate it here in the diagram. Here's the included angle between B and C, and we're looking at the angle that is opposite the side we're looking at. Okay, so I can actually find the other two formulas for the law of cosines here. Let's try it for side B here. Okay, so we take B and we square it. Now that's equal to the sum of the other two sides squared. So we take A squared and C squared. And then we're going to subtract 2 times the product of A and C. So A times C, so 2 times those two lengths that we were just looking at. Now times the cosine of big B, the cosine of the angle that's opposite the side that we're looking at. Okay, now if you're looking at this, it's kind of similar to Pythagorean theorem, and because we're not dealing with a right triangle, we kind of have to account for that. So we're taking, A squared is equal to B squared plus C squared minus just a little bit, okay, to account for the fact that we're not dealing with a right triangle. I guess you can think of it that way. And then finally, if we take a look at C, so the side length C, if we square that, that's equal to the sum of the other two sides, so B squared and A squared, minus 2 times their product, so A and B, times the cosine of big C, so the angle that is opposite the side that we are solving for. So let's actually apply this now here when we are asked to find a length. So I want to find the length of x, so I'm going to write x squared. So x squared, remember that's kind of like your A or your B or your C term, and that is equal to the sum of the other two sides squared, so 7 squared and 8 squared, minus 2 times the product of 7 and 8, those other two sides, times the cosine of the angle that is opposite the side you're trying to solve for. So cosine of 120 degrees. Now I can solve for this and just do a little bit of mental math here. I have 49 plus 64 minus 56 times 2 is 112 times the cosine of 120. So we have x squared equals, what is this, 113, and minus 112 times the cosine of 120. So that's going to be negative 1/2. And if I solve here, I have 113 plus 56. That gives me 169. So the square root here of 169, that gives me 2 solutions, but I'm going to throw out the negative because I'm dealing with the side length of a triangle. So I end up with x equaling 13. And of course you could always plug that right into your calculator up here as well, but you'll end up with x equaling 13. Just remember that you can't just plug this in, you have to take the square root of that value. Okay? All right, now finding an angle is pretty similar. Here we just follow the law of cosines again. So in this case, I can solve for any of those particular angle measures because I have all of the side lengths here. So let's say that I wanted to solve for angle B. Okay, now I would use the side that's opposite angle B here. I would use that 5, and I would set up 5 squared is equal to the sum of the other two squares, so 3 squared plus 7 squared, minus 2 times the product of those two, so 3 times 7, times the cosine of B, that's the angle we're looking for. So if I want to solve for B here, I need to subtract 3 squared and 7 squared. So I end up with 25 minus 9 minus 49. And then I have to divide out this term here, right, to get the cosine of B. So divide out negative 2 times 21, and that'll isolate the cosine of B. So in the numerator here, I have 16 minus 49, so negative 33 over negative 42. equals the cosine of b. Okay, now if I want to isolate b, I would take the inverse cosine on both sides here, and I have b equals inverse cosine of 33 over 42. So that is the exact value for b, but if I want to approximate that, I'm going to type that in my calculator, and I end up with an approximate value of 38.2 degrees. Okay, I'm going to round to that tenth here. All right, now I want to solve next for angle A. Okay, so for angle A, I'm going to set up really similarly here. I'll have the side opposite angle A, so that 3. So I have 3 squared is equal to the sum of the other 2 squared. So 7 squared plus 5 squared minus 2 times their product, 7 times 5, times the cosine. In this case, I'm solving for A, and again, it's opposite that side 3. And then I just solve again for the cosine of A. So I'm working on isolating cosine of A, so I'd have to subtract these two terms here and then divide out that negative 2 times the sine, times 7 times 5. So we have 9 minus 49 minus 25 all over negative 2 times 35, and that will equal the cosine of A. So I end up with negative 40 minus 25, negative 65 over negative 70 equals the cosine of A, so positive 65 over 70. So I'm going to take the inverse cosine here of 65 over 70. I guess you could simplify it too, but it doesn't really matter in your calculator, and that'll give me A. So inverse cosine of 65 over 70 gives me 21.8. Okay, so if I have A is approximately 21.8 degrees, and I also know that B is approximately 38.2, I can solve for C, now that I have those two angles, just by taking 180 and subtracting, B and A, those measures, and I end up with 120 degrees. Now, I don't really like the fact that I'm getting 120 degrees here, without showing it exactly, but that's okay here. You could, of course, solve for angle C here by using the law of cosines one more time, and you will get the exact answer and that exact value actually for 120 degrees. Okay, last up we have number 5 here, which is just an application problem for the law of cosines, and it starts off kind of seemingly tough, but it's not too bad. So it says 2 trains leave a station on different tracks. The tracks make an angle of 125 degrees with the station as the vertex. So here I've got a train station. It's so cute. Look at that. And the tracks make an angle of 125 degrees with this station. So not great at drawing obtuse angles here, but that could represent the 2 trains on their tracks. And this angle has to be 125 degrees. Now the first train travels at an average speed of 100 kilometers per hour. The second train at an average of 65 kilometers per hour. How far apart are the trains after 2 hours? If we're asking how far apart the trains are, we're actually looking for this segment length here. So I'm missing this segment, which means I need to know the 2 segment lengths here. Since they are traveling for 2 hours and they are traveling at 100 and 65 kilometers respectively per hour, then this segment here could be 200 kilometers, since they've traveled the full distance of 200 kilometers after 2 hours. And for the other guy, we've only traveled 130 kilometers. And now we're using, again, the law of cosines here because we have a missing side and we have an angle opposite this. Oh, I should have mentioned this earlier. The law of sines here doesn't work. Hopefully you're recognizing why the law of sines doesn't work and why you have to use the law of cosines. And in fact, it's for all of these problems here. You have to use the law of cosines because we don't have one full ratio. Remember, you need to have an angle measure and a side opposite that in order to use the law of sines. And in this case, we also don't have that ratio given. So I must resort to using the law of cosines. So to set up the law of cosines, I say x squared is equal to the sum of the other 2 squares, so 200 squared plus 130 squared, minus the product, 2 times the product of those 2 sides, so 200 times 130, times the cosine of the angle that's opposite the sine I'm searching for, so cosine of 125. And now this is something, if you want to solve for x, you would just literally type all of that right into your calculator and then make sure you take the square root of that particular value. But that is the end of the lesson. I just wanted to show you one problem where it looks kind of maybe like a tough one, and then it simplifies to something easier. Again, make sure you understand the difference between when you can use the law of sines and when you can use the law of cosines. So law of sines must have at least one full ratio filled in order for you to use the law of sines. All right, that's the end. Nice job. I'll see you guys tomorrow.